Hello, my name is John Bradshaw, and I am going to present our work on constructing a 3D finite element model for simulating blast wave transmission through a human ear with a two-chambered spiral cochlea. To begin with, the ear is the organ responsible for hearing. Sound waves entering the ear canal are detected by the tympanic membrane. Pressure fluctuations vibrate the tympanic membrane, which in turn leads to the vibration of the ossicles in the middle ear cavity. The displacement of the stapes footplate at the end of the ossicular chain induces pressure fluctuations in the fluid-filled cochlea that vibrate the basilar membrane. Hair cells in the basilar membrane are very sensitive to the displacements of the membrane and are responsible for converting these mechanical vibrations into electrical signals sent to the brain through the cochlear nerve. The sensitivity of the ear to pressure fluctuations means that rapid, high increases in pressure, like blast overpressures, cause major displacements of middle ear and cochlear structures. Large displacements of the ossicular chain lead to large pressure fluctuations in the cochlea, and the resulting high deflections of the basilar membrane can cause damage to the hair cells in the cochlea and subsequent hearing loss. This is a serious problem for people like military service members who are exposed to disproportionate amounts of blast waves during their careers. To understand blast overpressure-induced hearing loss, it is important to know how the basilar membrane displaces in this situation. However, observing displacements in the cochlea non-invasively during blast wave exposure is extremely challenging. Finite element modeling provides a useful way to gain quantitative information about the inner ear response to pressure waves. Our lab published in 2020 a 3D finite element model of the human ear with a simplified cochlea. The cochlea is straight and has two chambers separated by the basilar membrane. This model was used for transient analysis of the ear during blast wave exposure and yielded results for cochlear pressures and BM displacement. The two-chambered spiral cochlea model aims to improve the straight cochlea model. It has three primary goals. First, this model will change the cochlea to a more anatomically accurate spiral shape, as the human cochlea is a spiral with 2.5 turns. We also want to see if the spiral shape affects the pressure fluctuations in the cochlea and in turn the vibration of the basilar membrane. Finally, this model is a precursor to a future anatomically correct model we hope to complete with 3 chambers in the spiral cochlea, separated by the basilar membrane and Reissner's membrane. Thus, the two-chambered spiral cochlea model is very important for the continued understanding of inner ear behavior during blast overpressure exposure. We aim to accomplish our goals by changing the finite element straight cochlea in the full ear model to a spiral cochlea that could be used for blast wave analysis. This is the two-chambered spiral cochlea finite element model we developed. The ear canal and middle ear are identical to the previous model. This cochlea has 2.5 turns in its spiral, with the flexible basilar membrane in the middle, flanked on both sides by bony supports that do not move in the simulation. The base of the cochlea is where pressure waves enter the first chamber in the cochlea, the scala vestibula. The second cochlear chamber, the scala tympani, is connected to the scala vestibula at the apex of the cochlea, where the basilar membrane ends. The model was run using ANSYS Workbench. A fluent and mechanical coupled simulation was set up using the system coupling service in Workbench. The tissues of the ear were mostly specified as viscoelastic, with a beta damping factor or prony shear relaxation model. The input pressure waveform was applied at the entrance of the ear canal, marked by P0 in the top figure. The main interest of this model was reporting the displacement of the stapes, pressures across the basilar membrane in the cochlea, and basilar membrane displacement. The bottom figure displays the locations in the cochlea where pressures were measured throughout the length of the basilar membrane. Membrane displacement was recorded near the pressure monitors as well. Any differences between the results of the spiral model and the straight model using the same input waveform are very important, as they indicate a change due to the shape of the cochlea. We successfully obtained results for the stapes movement, cochlear pressures, and basilar membrane displacement in our model. The movement of the stapes is described in this plot. Stapes displacement in the model is induced by the input blast waveform at P0. The piston direction is normal to the stapes footplate, and negative piston displacement indicates that the stapes is pushing into the cochlea. The superior and anterior displacements indicate the rocking motion of the stapes. The piston displacement is much greater in magnitude than the other directions and is most responsible for cochlear pressure input. These results lined up very closely with the stapes movement reported in the straight cochlea model. These plots show the pressures across the basilar membrane at different distances from the base of the basilar membrane. The black lines indicate the pressure in the scala vestibula, while the red lines are the pressure in the scala tympani. At 2.5 mm from the base, the pressure in the scala vestibula is significantly higher than the pressure in the scala tympani. As the pressure waves travel further into the cochlea, the pressures across the membrane begin to equalize, until at 28.25 mm from the base, the pressures on both sides of the membrane are nearly equal. This trend was observed in the straight cochlea model as well, and is partially responsible for the different behaviors of the basilar membrane throughout the cochlea. Worth noting here is how high the magnitude of pressure in the scala vestibula is. Close to the base of the membrane, the scala vestibula sees pressures of up to 175 kilopascals, which is significantly higher than those reported in the straight cochlea. This difference is probably due to the spiral cochlea having smaller chambers than the straight cochlea model, which naturally leads to higher pressure buildup. The displacements along the length of the basilar membrane are displayed here. This is the movement of the membrane between the two chambers of the cochlea. Displacement into the scala vestibula is positive in these plots. The vibration of the membrane near the base of the cochlea is shallow relative to the vibrations in the middle, due in part to the base basilar membrane's stiffer material properties. The displacements are much higher than normal due to the blast wave and would cause damage to the hair cells. Overall, the basilar membrane displacement from base to apex here is similar to that of the straight cochlea model. Interestingly, the spiral model basilar membrane displacements closer to the apex of the cochlea seem to be responding to a low frequency signal in addition to their higher frequency vibrations. The longer negative wave, appearing at the start of the 18 mm, 23.25 mm, and 28.25 mm displacements, was not observed in the straight cochlea results. We also recorded the transverse displacement along the basilar membrane. This is the movement of the membrane towards the center of the spiral of the cochlea, not into either chamber. This movement is significantly smaller than the vertical displacement of the membrane, as you can see from the y-axis scale. The dotted line is the transverse displacement in the straight cochlea model, while the solid line is the displacement in the spiral model. Relative to the spiral model, the straight cochlea hardly has any transverse displacement at all, indicating that the transverse displacement is dependent on the spiral shape of the cochlea. Given how sensitive hair cells are to the movement of the basilar membrane, transverse displacement may be an important factor in the inner ear response to blast overpressures. Finally, the pressure contours in both the straight and spiral cochlea models were recorded. Figures A and D are at 2.5 mm from the base, B and E are at 18 mm, and C and F are at 28.25 mm. Figures A, B, D, and E have different legends for the scala vestibula and scala tympani, given that the pressure differences across both chambers are so extreme. In the straight cochlea model, the highest pressure is concentrated around the basilar membrane throughout the length of the cochlea. In the spiral cochlea, at the base and middle of the cochlea, the highest pressure is concentrated around the basilar membrane, but near the apex, the high pressure center appears to have shifted to the side. This corresponds with the increased magnitude of transverse displacement in the basilar membrane towards the apex of the cochlea in the spiral model. The results of the spiral cochlea model showed much higher pressures within the cochlea than the straight cochlea model. Both models had similar trends regarding the pressure difference across the basilar membrane and basilar membrane displacement variation. The spiral model alone showed transverse motion and asymmetrical pressure distribution near the apex of the cochlea. Because the spiral shape of the cochlea is the only substantial change in this model, it can be assumed that the spiral shape is responsible for these developments. So we conclude that the spiral structure of the cochlea is an important contributor to cochlear pressure and basilar membrane movement, and an essential part of any model aiming to accurately simulate high-pressure cochlear mechanics. Thank you very much for listening.